All right, guys, let's get started. Okay. So this week I still want to cover some more basics about machine learning so that you can start to at least try to build some very simple language model, not large language model, but simple micro hello world model. Okay. Just a quick recap. So this is what we did last time. Okay. So if you remember, we're talking about this traffic example, very simple one, but it's a very straightforward scenario where you see how do we define the problem. We talk about this is the target you're trying to predict, and these are the input features that's related. Okay, and then we supply data there so that machine can learn it. And once we decide to learn it, we will figure out a model. We decide to use a linear model first, and then we run the results. It works. We also showed you how do you do everything with code, right? So we use a library called sklearn or scikit-learn. That's the most popular library in machine learning with Python. So you gave all the sample data. That's where you do the model selection, and then you call something called a fit, and then providing the input data, output data, and then you train everything. And then from there, you can start to make some predictions. Okay. After that, we also thought that, well, the model isn't that accurate because we do know that the reality, the traffic doesn't always go through linearly, right? So you have different curve, different situation. That's when we realized, well, we need to maybe change our model a little bit. Instead of using linear model, we use the curve, we use a polynomial model. And we also talk about, well, maybe there are other factors we want to bring in. We bring extra columns, the day of the week, weather, accident, all of those, so that's how we can make the model much more comprehensive, right? So if you look at the final code, right, so we actually modify the input data to include two columns, two features. One is the time of day, and the other one is the day of the week. And then for the output, we try to predict the same thing, but now we obviously have to supply more data because we have to cover different days. And then we use two model to compare, right? So the linear model, and also we use the polynomial model, right? So if you run it, that's the result you see right here. I just put everything back to cursor so that in the future we can run everything easier. So yeah, you can see all the different results. From the data, you can see eventually if we use multiple columns, multiple inputs with a polynomial model that just describes situation a lot better. Okay, so that's where we were last time. To summarize, if you think about to make a machine learning problem, these are the major steps. Okay, that's just what I mentioned. You start from defining the problem. Okay, what is the target you're trying to predict or analyze, and what are the things related factors that's going to affect those target. Define those first, and after that you have to provide data. Otherwise, there's nothing you can learn. And also you decide certain kind of algorithm. And this is where you need a lot of experiences, right? You're looking at the data, you look at the problem, you should have some, first hypothesis or assumption, certain model is going to work for this one. Obviously, you need to know enough models. That's the key part about machine learning. If you're going to take some of the machine learning courses, you will be able to learn a lot more different kind of algorithms and different models, different algorithms have different kind of strengths and weaknesses. You often need to make some trade-offs and make the right decision. And once you select a model, supply the data, you can train it, and then finally just use the model to make predictions. Okay. But then we also talk about based on that example, if you don't see the result to be very good, not very accurate, so what do you do? Normally, one thing to think about is to give you enough data, because if you don't see enough data, there is no way you can learn or figure out some of the special patterns. You also need to think about if you want to add more features. Like we talked about only one time of the day, and what if we want to add the day of the week, traffic, weather, all of those. Those make the situation better. Most cases, obviously, the more feature you add, the better. But sometimes I also mentioned that you don't want to add too many, okay? Because you have too many features, sometimes it's called overfitting. It makes the problem more complicated. Maybe some of the features are not that, significant. Or like if you do have a lot of features, Make sure you also have enough data. Otherwise, still not very meaningful. Right? So the feature, having more, is good. That means you can define the problem more accurately, but make sure you have the data to support it. Okay, and then if you still don't see the result being improved, think about changing different model, different algorithms. So normally these are three things you do, or you play around with to do experiments to see how you can get the best results. Okay, so that's where we were last time. So moving forward, okay, I want to introduce a new type of machine learning, which might be a little bit more common to use. It's called a classification. Okay, the first case, like the traffic example, we use something called the linear regression, polynomial regression. To summarize, it's called a regression model. Okay, where you can think about it's used based on this mathematical model or a function, a formula, and then try to describe certain situation, and you can get some data. Where classification does something a little bit different. That is trying to classify certain things. Okay, so we'll come back to summarize the difference between classification and regression. But let's just start with a very simple or very famous example. There is this example called iris flower dataset. Okay, so I put a link here. So this is a very classical kind of a statistics problem, but later on people use this one to run as a machine learning or classification example. So basically what happened here in the very early days, some of the biologists, they did some measurements and statistics about this iris flower because they found there's three different types of flower. They have three different names like the Setosa, the versicolor, and obviously they're the same type of flower, but a different species. I guess that's how they call it. And obviously they look different, right? So the biologists did a lot of measurements. They go to different places to measure different kind of plants for each species, and then they got a lot of data, so that they're trying to differentiate. Okay, how do we decide what type it is, right? So if you look at that data set, and you can see where is the data set? Right here. Yeah, right here. So this is the initial data set they collected. So 150 records uh, under 5 attributes. Okay, so they have the sepal length and sepal width. They have the petal length and petal width. Okay, I can't tell you what is sepal and petal. You guys probably learned that from biology, but that doesn't matter. Probably some part of the leaf or flower, whatever they call it, it's just different shape to measure the flower. So based on the length and width, you can see they're different across different species. So Centaura, you have a 50 measurements all the way to here. And a versicolor, they also have another 50. And then finally, they have a Virginica. Okay, another 50. Okay, so total 150 records, measurements. Now, if you look at the data, you can probably see some similarities. It looks like, for example, the first one, this paddle width is pretty small, where the other one, like the versicolor one, is a lot bigger, right? And then the Virginica also is even bigger. So you can probably see some of the patterns. And then clearly, if you know these plants enough, okay, looking at this measurement, you can probably make a decision. Okay, so the problem of having some kind of input data and then decide which type it is, which species it is, that process is called a classification. So we're trying to classify, want to put you to one of the groups we know. Okay, so that's called a classification. All right. Now, if you look at this table here, that if you go back to think about the machine learning process, right? So we still have this target. That's the one we're trying to predict, okay? Whether it's Centosa, versicolor, or Virginica, right? So three types. That's the target. And then we believe that the features related are these four columns, okay? Sample length width, petal length width. So that's our problem. Target, inputs. Okay, that's step one. Step two, do we have enough data? Yes, we have 150 records right here that we can use. It's already the real measurements. Very good. So based on those, we can start to conduct machine learning, that machine to figure out the relationship, the pattern, so that we can make decisions. Okay, so let's go back to the code. Okay, so I'm gonna put this one into, so we'll call it a classification demo. All right. So I'll get the data first. Okay, input data. Okay, so they can do this fairly quickly, but we're gonna copy some of the data here. Okay, so I'm not gonna do the 150, but I will just do some of those. Oh, so they're pretty efficient. Okay, very good. So I don't know how they get the others. Um, okay, not sure if they probably have some data, but this is good. This is good. Okay, I'm gonna check 4.9, 4.7. I think that's the one they provided here. 4.6, no. 6.3. What is 6.3? Um, all right, so I'm not gonna use this, but it looks like it's this first three, 3.2, 1.3, 0.2. Yeah, so these are the first three rows. Okay, let me just get one more. Because this is a very classical data set. So obviously AI also had it. Okay, so I'm going to start with four records. I don't have to do the whole 150. Okay, and then I'm going to do from here 70, 70. Is that the correct data? Yes, that's the correct one. Oh, sorry. And let's just do this. Also, I'm going to correct just a 4, 5.45. 1.3. Yeah, that's all correct. Okay, so this is great. Okay, otherwise I have to just type everything and put all the comma. And finally, let's do the third type. I'll pick the first four, which is 6.3 and the 3.3, 6. No, that's not right. 6.0. Yeah, that's the one. Okay, so 6.3, 2.9. All right. Anyway, so we can do this one fairly quickly. So we just basically move the table from here. Every type I choose just the top four measurements. Okay, so that's the input data. For the output data, all right, so obviously you are going to provide all the types. Okay, so the first four are all the CentOS have type. And I don't know if they can figure out this one. And what about, yeah, so they see, they can just get everything. Plus, all right. And then lastly, it should be, no, this is not right. So this one, Jenica. All right. So a total of 12 records. Okay. So I'll just break them so you can see them clearer. Okay. So once again, these four records coming from the first type. So we actually label the output data. So in scalar or secular, you just have to split them. You can't put them in the same table. So one list, you talk about input, and one list, you talk about output. All right. So all we're trying to do here is trying to move the data from here and to the Python code. All right. So that's step one. Okay, now step two, once we have all the data ready, sample ready, we're gonna choose a model. Now, this time we're gonna choose a different one. Last time we talked about linear regression, polynomial regression. This time, since we're talking about different problems, it's called classification. There are a lot of classification algorithms. And the most famous one is something called SVM. Okay, so this has been done back in, as you can see, really early. Okay, a lot of the machine learning algorithm, if you look at history, see it was really proposed in the 80s, 90s, and initially 70s. Okay, a lot of those are coming from a math department. Okay, but those are not very useful until recently because in the past 10, 15 years, as I told you before, we just had a lot more data now. In the old days, we don't have a lot of data, so having this algorithm isn't that much useful. So SVM is called a support vector machine. Okay, so I really can't explain you all the mathematics behind it, but what they're trying to do is that we have, some data points here, okay? And if it's 2D, you can still kind of write them on the axis like this. Now we're trying to define a function, okay, just like the first example, you do a mx plus b, whatever the function is, you want to define some kind of function so that you can draw a line there. That way you could use a line to split the data into two or multiple different groups. Now, if you see here, this right line here does a great job because all the black goes to one side and then all the white goes to another side. The blue one also works, okay, on the left-hand side, and then the rest go to the right-hand side. The green line is not good because they kind of mix the black and white somehow, although they have this part here clearly split. So as you can see, when we're talking about a classification algorithm, we're not trying to do the best matching. We're actually trying to just figure out a way to split them and split them as much as we can, right? So like a quick question here. If you see this red line and the blue line, okay, they both did a great job to split everything. Which line is better from a classification point of view? Or which line is preferred? Yes. Red one, why? Yeah. Yeah. Exactly. It's because see, we did a better job because we clearly spread the space and then you have a lot of margins here, right? You got an extra space. Just in case you got some new data points, and more likely that new point probably will not cause any conflicts. Where if you use the blue one, even though you do split the current nodes, but what if you have a new points that just getting very close, you might have some kind of overlaps. Okay. It's just your intuitive. Okay. But obviously you can also explain that from a mathematical point of view. So this is a little bit different from regression. When we talk about regression, best fitting, you want the line to cover the points as much as you can. You don't want them to be so too far away, because if it's too far away, then the number you're calculating won't be very accurate. But now we're talking about a classification problem. We're trying to split them, we're trying to group them, and as much as we can. Okay. We really want to find them their differences. Okay. Anyway, so that algorithm is called SVM. In other words, if you give me the data, I can eventually generate some kind of function that can split the points. That's what the SVM is trying to do. Obviously, this is a much more complicated situation because this is only a 2D situation. And they think about, now we have four columns. That's a 4D situation. How would if it's 3D, you do a plane, and 4D, how do you describe those? So it's a really complicated. All right, but doesn't matter. The code will do that for us. All right, so this is what you do. So from sklearn import, we're gonna do something called SVM. All right, so that is a model coming from the sklearn or scikit-learn. So after you have all the data, and we're gonna define that model just like the first time. Okay, they already wrote it for it first, but I'm gonna still repeat it. Okay, model equals svm.svc. That's where we define the model. All of this you can find from the sklearn documentation. It's not very difficult. Okay, and then model.fit. Okay, fit means training, to learn, input data and output data. All right. And yeah, they pretty much read everything for us. But I'm going to use this one so that save us some time. Okay, but the process is exactly the same as the first one. Okay, import data, define the model, fit and train, and then predict and train. Here, same thing. We use SVM, input output data, and define the model, fit and train, and now you can predict, and you can predict results. Okay, now let's test it. So I'm gonna try some new data. Okay, so I'm gonna go back here. I'll pick this one, which is not really used in our training data, right? So this is the Sentosa. So I'm gonna bring this one over. Okay, yeah, I'll just use one first. Okay, remember this is from record 20. Okay, we only use the 1, 2, 3, 4. We never seen this before. So now if I run this code, oh yeah, it's already printed. Sentosa. Okay, the very first type. Okay, you can try more. Let's try the second type here. Also something we never seen before. And let's also try one more. All right, so we run this code again. You will see the first type, second, and the third one, uh, which is exactly correct. Okay. However, as you can see, we actually only used 12 data points. We didn't use all the 150. If you can use all the 150, I think the result would be even better. But clearly, just with 12 data sets already give us enough samples so that they can figure out a correlation. So that is the iris flower example. You will find this example in most of the machine learning tutorials or courses as a very classical example. It really demonstrates what the classification is. All right. And then the model we're using is something called SVM, support vector machine. Okay. Once again, if you want to dig into the mathematics behind it, probably you can find some of the resources. I think they still use a lot of calculus stuff. Okay. All right. So that process is called a classification. Okay. So now I want to bring the question now. If you see this example and then this first example, we already told you the first example on predicting the traffic value is called a regression. Okay. Remember the term regression, very important. And then today we just look at another type of machine learning called a classification. Can anyone summarize the difference between regression and classification? What are the major differences you see between the two type of algorithm?
Think for regression is deal with the continuous data set,
Yes,
and for the classification, deal with categorical that actually.
very good. Yeah, so that's the most accurate definition. Okay, so they both were trying to predict certain things. Okay, trying to get some answers. But the first one is getting a continuous value. As you can see, we provide all the numbers. When you're calculating the traffic, you can see you got all these little very detailed decimal numbers. Okay. You tell me the traffic is 1, 2, 3, 4, 6, 8, 9, and then they're going to tell you for 7.2, 6.6, 3.1 continuous. It doesn't matter if you provide that before. I just want to give you a very accurate calculation based on that model I choose. Okay, that's called regression. So regression means that we'll give you all the data, you do a model, try to try to fit all the data we have. That process called regression. And once you have that one, you can use that function or line to predict any kind of points along the line. But for classification we look at today, we don't want to continue the data. When you try to do the classification, you must give me one of the options. In this case, I have three options only: Sentosa, Versicolor, and then Virginica. You can't tell me a 1.5. You can't tell me a 2.5. That doesn't make any sense. I just need one of the types. Okay. Just give me a category. Okay, so that's the difference. Okay, so if you understand this one, you really have to always think about what our problem is. You're trying to predict something. Is that a regression or is that a classification? Once again, you think about you go to Google Map and then you try to look at the future traffic. They give you the traffic to LAX to be 1 hour 20 minutes, 1 hour 50 minutes. Clearly, that is a regression because you're trying to get a very accurate number of minutes. Okay. Or if you, what other example? Okay, so some of the very classic example, like spam, like in email. Most of the email today have a spam detection system, and they automatically move some of the email to the spam folder. How do they do that? Well, they do a classification. Any email, whether it's a spam or not, yes or no. You can't tell me it's like half spam, half not. No, it doesn't make sense. Okay, so that's called a classification algorithm. All right. A lot of time you have to decide which one, and then you follow some of the algorithms. For classification algorithm, there are also many algorithms. Here we only showed SVM. There will be something else called a decision tree, random forest. There are tons of those. Okay, so if you go to the sklearn, and then you should be able to find all those yeah, see, they give you classification. Just for classification, they gave you so many different algorithms. And regression, they also give you a lot of things. Okay. There is a third type called clustering. Okay, so we'll probably talk about that next time. But the most important thing, I would say, the classification and regression. Okay, they're trying to do just from this graph, as you can see, it's give you a very good visualization. They use different kind of algorithm to split the groups. And this one, they use a different algorithm to give you a kind of a description on what the data should be. Okay, so that's the difference. For clustering, we can talk about in the future. It's almost the same as the classification, but for clustering, we don't know the types. Okay, so for example, for the iris flower, now I tell you there are three types. I actually know the label. Okay, and so I gave you all this input data you can train. Sometimes I don't, for example, I seen that there are differences, but I don't know how many types there are. So I don't know this column, but I only know the measurement. And I will tell the machine learning, well, please figure out some types for me based on the data. Um, Give me two type, three type, or four type. So then they will, based on the data, they will actually build the types for you. That's called a cluster. So that's going to involve another term. You might heard something called supervised learning versus non-unsupervised learning. So when we talk about supervised learning, that means when we're trying to learn, trying to train, trying to fit, we supervise you how you learn it. The most important thing we're trying to supervise you is the target. I'll tell you these four, they are Sentosa. Just know it. Remember, that's the facts I gave you. So that process is supervision. These things I tell you, they are versicolor. Just remember it. Okay, I already gave you the answer in the input data set. That process is called a supervision, or this type of machine learning is called a supervised machine learning. Traffic, same thing. I told you the 6 o'clock the traffic is 2, 10 o'clock traffic is 10. That's the facts. Just remember it. That's called a supervised learning. Okay, so anytime when you are forming your input data, as long as you have this thing given, okay, that process is called a supervised machine learning. Okay, most machine learning problems are supervised because if you have this one, that gives the machine the most fundamental facts to rely on to learn things. Okay, but sometimes you just don't know what's going on. You have very complicated things, or we don't have things labeled. Okay, you give me a lot of data, I don't know what this type is. In that case, you could consider to use unsupervised learning, and the clustering, that's the most typical unsupervised learning. So, but I would say the first two are much more common and much more useful. Okay, so we will probably come back to cover the clustering in the future. Okay, but from here, I want to show you one more example today on the classification. Let's do something a little bit more practical. All right. So I was thinking to build maybe oh, by the way, this is also kind of a visual differences between the regression and classification. Okay, regression, best fitting, classification, we're trying our best to split them as much as we can. All right. I want to start with another example on doing a little simple game to play like rock, paper, scissors. Everyone can write a Python code, Java code to do the terminal version that is the input. You'll play with a computer or play with a human. Let's probably try to build a computer like player that can play rock, paper, scissors very well, so that hopefully the computer is smart enough to learn things. Okay, so to getting started, I'm gonna first create a quick version of rock, paper, scissors. All right, so I'll just use AI to do it. Okay, because this one doesn't is not very much difficult. All right. So write a simple Python terminal based rock, paper, scissors game that allows a human player to play with the computer. All right. It's a pretty simple game, so I'm gonna just use AI to do it. And then by the way, if you don't know, okay, this tool is called a cursor. As you can see, the difference between the cursor and using ChatGPT is that they work with your IDE directly, and they put all the code changes to the files like this. That you can track the changes, you can make changes directly. But if you ChatGPT, then you have to send a prompt, they generate the code, you copy it back here, and then something wrong, you go back there, back and forth. That's not going to work, okay, for the large scale. So that's why you want to use some of the dedicated coding environment. I'm sure the Copilot something, probably does something similar, but obviously I think a cursor is much more popular. Okay. So anyway, you look at a change, and if you like it, just accept it. But let's quickly go through this one. Okay. They have import and time and for random. This is to get a computer choice. Right now they just do a random choice, right? And then here they are asking for the user choice and just do the input. And then here, they determine the winner. Okay, so they have their way to decide the winner. Okay, so this is pretty simple logic. If you rock and scissors and then rock win, paper and rock and then paper win. All right, and then this is display the results. Play the game. They have some prompts here to print. Definitely a lot more things than I would write, and then much more detail, right? So let's just try to run this one. I think this one should work. So we are going to oh. Let me try to run this one. All right, so they have some kind of a prompts. Okay, looks like you guys should be able to see it. So welcome to rock, paper, scissors. Play against the computer and see who wins. So current score 0-0-0. Enter your choice. I'll do rock. Oh, see, they have a very nice animation. They even do a computer syncing. That's for sure something we will probably won't do. And I choose rock. Computer's paper, so computer wins. Okay, but I could play again. Yes. All right. So I will do paper, computer syncing. Computer wins again. Yes, I'll do paper again. And computer still wins. I'll do paper one more time. Ah, okay. So there's something wrong. I'll just sort okay, now I win. All right. So right now the score is I won't play. So score is 1-4-0. Okay. So pretty simple one. Okay, but I want to make some changes, okay, because I just don't ask if I want to play or not, just always yes. And if I want to quit, provide a input option to quit. So that way it's easier because I don't like it. I want to show you that with a cursor, you can start make changes. Once you do that, and they will start to make the changes based on this. As you can see, they actually highlight all the changes from the code. And you can review that if you think that's correct, and we're gonna keep it. Okay. So now let's try to run this again. All right, see, rock, paper, scissors, I'll do rock. All right. And they still want me to press enter. Okay, so that's but better. Okay, better than typing the yes or no. And then I do rock. Okay, quit or press enter. Okay, so um that's okay. But also let's use our PS to input. Okay, otherwise it's typing too much. All right. All right, so they make some changes. So you don't have to do all of those, but they still know how to map those to the full name so that they can do all of the winning check. All right, so let's run the game again. I do quit. All right, let's run this one. Okay, this time it's a lot easier. All right, I do paper. All right, I'll do scissors. All right, yeah, again. So please remove the step to ask, quit, or enter. Just go to the next input prompt. Add a queue for quit option. They should be able to figure it out. All right, what's gonna keep it? All right, so let's see if that works. Okay, yeah, so they have a queue option. So rock, paper, scissors. All right, and then quit. That's quit. All right, so a lot better. Okay, but they did a pretty good job. Okay, so this one is fine. Okay, pretty simple. Just the we do input. Now the computer get their choice. Okay, and then they just determine the winner. Okay, so right now the computer uses a random option. Um, that's pretty much a okay strategy. All right. So what we want to do now is try to improve the computer's strategy. Now the strategy we're going to use here is somehow we're trying to learn the pattern from the human players. Okay. So think about when you play rock, paper, scissors. There might be some situations that you want to follow some kind of pattern. For example, you want to show certain things in a row, you want to show more papers, or you want to show do the switch like with a certain kind of a sequence in your mind. Okay. But most of the time we just play, just randomly. But let's say sometimes people do play with a very clear pattern. Now, if the computer can capture that pattern, and then very likely you can, start to beat the other player because then you can predict what's the next gonna come. Okay. So the problem we're trying to do here is how do we predict what the human player is trying to play next time if there is a pattern. Okay, so that's the little engine we're trying to improve here. Okay, but going back to this machine learning problem. Okay, so we follow the same thing. I'm going to draw the table. All right. So what we're trying to do for the target is we're going to predict what's the next. So next play. Okay, that's what we're trying to see. Okay, this part is easy. But what are the things that's going to affect the next play? What are the inputs here? Are the features? So you play with another guy, you're trying to predict what he's going to do next time. So what are the features are things that could affect his or her next play?
The amount of times they play a certain.
Yeah, the amount of time they play certain moves, right? Are choices, yes. The most recent one, right? So the recent ones probably matters more, right? So as I mentioned, if I do some kind of pattern, I do rock, paper, rock, paper. And then if you see another two rocks, then you probably know I'm more likely to do the paper, right? Or yeah, you mentioned something else, like I look at your overall play, okay? Overall play, you do this one a lot more than the others, then I may do adjustment, right? So yeah, so let's do a simple case, just the recent plays, okay? Maybe I'll just look at your recent two plays because just one is very hard to figure it out. Okay, so I look at the past, the recent one, and recent two. Okay. And I use that to predict what's next. Okay, so that's how we define that problem. With that one, and we need to start to supply um, the data. Okay, but here you got to first understand how this data is going to work. Okay, so for example, this is how I watch because every time you play, you can watch and you can store what the player is showing, right? So let's say the player is doing rock, paper, uh, rock, paper, scissors, rock, paper, scissors. Okay, let's say the player you see they're following this kind of pattern. Okay. Now, what we need to put into the table is this. The first one is a rock, and then the second one is paper, and the third one is paper. Once you see three, right? So then you can form one record. Okay, which means that if you see a rock paper here, the next one is gonna be strong paper. All right. Okay, every 3 plays gives you 1 record. If you only play 1 game, you don't have enough data. But after the 3 games, you can see the past 2 and then the current third one, and then you will be able to put something here. And then you look at the next one. So the paper, paper, and scissors. Okay, then you can put paper here, and scissors. All right. And the next one is paper, scissors, rock. Paper, scissors, rock. And you keep going. All right. So obviously, the more play you have, and then the more patterns you can see, the more data you have, and the model. Hopefully, if you are really following certain things, and then the machine learning will be able to always predict the next one. Well, first of all, what is the type of problem? Is this a regression problem or it's a classification problem? Are you gonna get a continuous number value or it just give you a category? Yes, category, right? Because you can only predict one of the 3 choices. Okay, so it is a very straightforward classification problem. Okay, even though it looks like some, you can use the numbers to represent, but it is a classification problem. Okay, so that's how we form the model. Okay, so this is just one way. You could definitely come up with other more sophisticated way to track history and to analyze it, but this is just a very simple way. Okay, based on the past to play, and then you actually do the try to do the next one. So. That means in our code, we need to basically add a way to track all the histories. So every time when a human get a choice, okay, as we do the determine the winner, right? Let's say after each time we determine the winner, we need to immediately record what the user choose. Okay, we need to put that into a list. So I'm gonna write, I'll have a play history. All right, I player history. Get all the data here first. And then we can use that one and try to predict the next one. So each time we see after a game, okay, as we determine the winner, okay, let's just record the user choice first. So something like this. Okay, we add that one here. However, the only thing I'm not sure is that these ones are using the user choice. I think they're all generating like the letters, strings. So we might need to change that into numbers if I remember correctly. So let me see. So the user choices, we provide this, right? So we do a choice, and our choice is just a letter, and the letter will go to become yeah, they will be uh, where oh yeah, there's this one here. So yeah, this is where we do it, and then the letters, and then they will then be translated to string. So we're gonna use the strings to record those. I'm not sure if the string actually works for classification. We might need to go back, change it to the numbers. Okay, let me do something very quick just to be safe. Okay, please change the internal representation of the uh, RPS into integers 1, 2, 3. Okay, let's try that. That way it will help us to run the machine learning. All right, so they make one change here. What else? Yeah, the computer functions also need to be changed. And then they probably also need to change how they decide the winner. Yeah, right here. Yeah, so they drop that map approach and then use the number to compare. Yeah, looks good. Let's try that. So I'm gonna try to play this again. So we still see the rock, paper, scissors. All right, that still works. And scissors. Okay, and winner wins and ties. Okay, so that should be good. All right, so now with that, as we are storing the user choice. Okay, so right here, the user choice. Yeah, so that becomes number. So that will be very safe. So we're just getting all the numbers. So that way the machine learning, like SVM, they can process it. Okay, so we're adding all the history here. Okay, one by one. Now, think about for the machine learning problem, we need a input data, we need output data. Okay, so as we play the game, we need to start to adding all the things into our like a data set. So every time you get a 3, and you can pick the latest one and the previous 2, and then you can add those into the number. So let's try this. So if the player for the size of the player history, is that how do you do the size in Python? Oh wait, so it's dot. Sorry. Wait, how do we do this? Check the size of the list in Python. Length. Okay, I think that's correct. If that one is greater equal than 3, all right. So what we want to do is get the latest one to the output data and the first 2 into um the input data. So we need to add this one and also the output. So the output one will be easy. So output data append. We want to get the latest one. Is that a negative one? Is that how you get the latest one? The last item in the Python list. Actually, you know what? Let's how to get the last item from a list in Python. All right, yeah, -1. Okay, so that gives you the latest one. So the latest one goes to the output data, and then the input data. All right, so that's going to be 2 items. Okay. So do we do the -2 and 3? How to get the second to the last item? Yeah, -2. So we add -2, actually -3. All right. Did this part make sense, guys? Think about that window here. Okay, you got it. The pass, you're going to process the last 3. This one is the output. These 2 are input. And if you see this, again, this is output, this 2 is the input. So we're just, every time when we're at the end of the game, we need to get all the data here to collect them. Okay. So eventually you will start to see the list getting longer and longer. So let's actually print it. Okay, so that you can see what's going on. So print input and print output. All right. So I'm gonna do log invalid. Okay. Log paper log paper. See, that's what we've been capturing. So log and paper. And another the next one is log paper, it's a rock. Okay, so basically in this case is 1, 1, 2, 1, 1, 2, and then we play for 6 games, and you can generate 4 data set. Okay, as game goes, you should see what's the output, what's the input. All right. Now, once you collect more of this, you can start to run machine learning, try to predict. Okay, so in this case, we're going to do something different. I'm going to import SVM. Now it's all random. What we want to do now is that I want to predict. Predicted next choice is we have to train it first. Okay, model equals SVM and a model dot fit. Each time I have to retrain it because I might got some new data. All right. And then I can then predict. So as we predict, we're going to use the past, the recent to history. So the recent to should be this and this. Right. All right. And obviously we need to have enough data. So if the length of the play history is greater than 3, then we can start to make this. Otherwise, it doesn't make sense. Okay. All right. So we got 2 situation. And then we're trying to predict the next move using the recent 2 plays. And then once we predict it, we're gonna give the opposite, right? So I'll just write this one. If this one is 1, we are gonna return 1, let's see, 1 is rock. So I predict you're gonna be rock, then I'll give you paper. If I predict you're the paper, I'm gonna give you scissors. Otherwise, I'm gonna give a rock because you're scissors. Okay, so I predict the next one, and then I give you the upper set. That's how we change the computer's choice. So you're building a little bit more intelligent one instead of using the random choices. Okay, that should work. But wait, so this one here, I think we're gonna get the first one. But let's verify it. So if this program works, okay, if you follow a certain fixed pattern, rock paper, something like this, if you play enough, then you're always gonna lose because every single time the computer will be able to know or predict what's your choice. So let's verify that. All right, so I'm gonna start follow my pattern. Okay, I'll do a rock. I'll do a scissors. RRS. Okay, just repeat that one. Right now, the first 3 games, I actually win twice and computer only win once. So RRS. Okay, we will repeat that one. So we do the rock. Oh, the number of cards has to be 1. Okay, so that problem is that we only actually seen like a 1 case you can't. So when you try to do classification, you must have more than 1 type to classify. Otherwise, it doesn't make any sense, right? So we might need to change this one a little bit. Instead of this one, how we're gonna do this? How do we know we have more than 1 types? All right. Maybe what I would do is I'll just give some sample data here. Okay, I'll do a 1, 2, 3 initially. It doesn't matter, and then we can provide some sample like a first. Okay, that will make the program easy. Okay, so you always have something to start with. All right, so we're gonna start from this one, and then later on, once you see enough data, the model can be retrained and can be changed. Okay, so let's try this again. So initially it doesn't matter. Okay, so rock, scissors. All right, so computer wins twice and there's 1 tie. So let's try that again. Rock, CSS. All right. Now I win computer like 2 twice, so it's pretty much even. Okay, but I keep doing the same thing. Rock, CSS. All right. So now you can see, I think the pattern started showing up. Okay, 1 1 1 3 3 1, 1 1 1 3 3 1. Okay, I would do more. Rock, CSS. All right. So now, like that's the pattern I mentioned. 1 3 3 1, 1 1 1 3 3 3 1, 1 1, and there's a pattern start repeat. From here, you're gonna see that the computer probably always gonna win. Okay, next 1 7 4. Okay, I'm gonna repeat my pattern. Rock, CSS. See, every single time computer wins. Rock, CSS. And the computer won another 3 games. So if I keep doing the same thing, and the computer will always be able to predict it. Okay, the reason is that if you look at all this sample data, sorry, the input data and output data, clearly there is a very strong pattern here. And that pattern weighs more so that the model actually picks it up. Okay. Now, I know, guys, this part of the code I did it really quickly. Okay, so there's some of the logic you got to go back and sit on. I might give you assignment, just try to implement your algorithm. But this is how you apply machine learning in practice. Okay, so a lot is the problem. As long as you want to predict, you want to make some analysis. Okay, you could start using machine learning to give you that kind of a guidance. But then the key is that you need to know how to define the problem, find the input output features, and provide the initial data, and then train, use the right model to train, and then predict and start to use. Okay, so if you understand this one, you can actually use this one for a lot of other different problems. Okay, any questions? All right, so I'll push this code to you and then you can take a look, okay? The best way is that you write your own algorithm and try to play around with it, okay? It's a lot of fun to do things like this. All right, so I'm going to stop here for classification because again, this is not a machine learning course. I just want to give you a very quick overview how it works, some basic coding, basic library to use. Okay, so hopefully we can start to use this one to build some of the real, like a little bit language model. If you think about the language models, I explained to you last week that the model basically does one thing, get an input string and then print the next word, right? So that process is also kind of a classification. You have so many words to choose which word to use to show you. It's a selection. It's a classification. All right. Okay, guys. I think we're gonna stop here, and I'll push the code, and then we'll talk about some other things on Thursday.